From the idea that stars twinkle because of their own light flickering, to the misconception that seasons are caused by Earth's distance from the sun, we're here to debunk these myths with scientific facts and evidence. Whether you're a seasoned astronomy enthusiast or just curious about the cosmos, this video will provide you with a deeper understanding of the universe and the fascinating truths that lie beyond these common misconceptions. Stay tuned as we explore these myths in detail, separating fact from fiction and uncovering the real wonders of our celestial surroundings. If you love learning about space and the science behind it, don't forget to subscribe, like, and turn on notifications for more exciting content. Myth: the Earth is flat. The belief that the Earth is flat is one of the oldest and most persistent myths in human history. It dates back to ancient civilizations when observational tools were limited, and the flat Earth concept was more intuitive based on everyday experiences. Some flat Earth proponents argue that the horizon appears flat, and they claim visual evidence supports a flat model. However, this myth is debunked through numerous scientific observations and experiments. One of the simplest proofs of a spherical Earth is the way ships disappear hull first over the horizon. On a flat Earth, a ship sailing away would remain fully visible until it became too small to see. Instead, ships gradually vanish from the bottom up, indicating a curved surface. Ancient Greek philosophers, such as Aristotle, provided early evidence for a spherical Earth. Aristotle noted that during a lunar eclipse, the Earth's shadow on the moon is always round, which could only be the case if the Earth were spherical. Additionally, he observed that travelers heading south could see stars previously invisible at northern latitudes, suggesting a curved surface. In around 240 BC, the Greek mathematician Eratosthenes conducted an experiment to measure the Earth's circumference. He noted that at noon during the summer solstice in Ceylon, modern-day Aswan, Egypt, the sun was directly overhead, casting no shadow. However, in Alexandria, about 800 kilometers to the north, vertical objects cast a shadow at the same time. By measuring the angle of the shadow in Alexandria and knowing the distance between the two cities, Eratosthenes used geometry to calculate Earth's circumference with remarkable accuracy. In modern times, photographs from space provide unequivocal evidence of a round Earth. Satellite images consistently show a spherical planet, and astronauts aboard the International Space Station witness the curvature of the Earth firsthand. Additionally, global navigation systems, GPS, rely on a spherical Earth model to function accurately. If the Earth were flat, the satellite's triangulation and navigation calculations would be significantly off, leading to navigational errors. The Coriolis effect, which influences weather patterns and ocean currents, also supports a spherical Earth. This effect causes moving air and water to turn due to Earth's rotation. In the northern hemisphere, it causes cyclones to rotate counterclockwise, and in the southern hemisphere, clockwise. On a flat Earth, such a consistent pattern of deflection and rotation would be inexplicable. Overall, the scientific evidence overwhelmingly supports the conclusion that the Earth is a sphere. The flat Earth theory, while historically significant as an early model of our world, fails to stand up to centuries of observational data and scientific advancements. Myth: we always see the same side of the moon. This myth, while technically true, leads to a common misunderstanding about the moon's behavior. It's true that we always see the same side of the moon from Earth, which is due to tidal locking. Tidal locking means that the moon rotates on its axis in the same amount of time it takes to orbit Earth. As a result, one hemisphere is always facing us, while the other remains hidden. However, this has led to the misconception that the far side of the moon is always dark, which is not the case. Both sides of the moon experience day and night cycles, just like Earth. The far side of the moon, often mistakenly called the dark side, receives just as much sunlight as the near side. During a lunar day, the far side is illuminated by the sun, and during a lunar night, it is in darkness. This cycle is crucial for understanding the moon's thermal environment, where extreme temperature variations occur between lunar day and night. The concept of tidal locking is also observed with other moons in our solar system, highlighting the interplay between gravitational forces and rotational dynamics. The phenomenon of tidal locking occurs because of gravitational interactions between the Earth and the Moon. Early in its history, the moon rotated more quickly. The Earth's gravitational pull created tidal bulges on the moon, and over time, these bulges acted as brakes, slowing the moon's rotation until it matched its orbital period. Exploration missions, such as the Apollo missions, have provided detailed images and data about the far side of the moon. Before these missions, the far side was a mystery, as it is never visible from Earth. These missions revealed that the far side has a different landscape compared to the near side, with more craters and fewer maria, large, dark basaltic plains. This difference is due to the moon's history and its gravitational interaction with Earth. Additionally, the far side of the moon has been a focus for recent and future space missions. For example, in January 2019, China's Chang'e 4 mission successfully landed a rover on the far side, providing unprecedented data and images. These missions continue to expand our understanding of the moon and its unique characteristics. In conclusion, while the moon is tidally locked to Earth, leading to us always seeing the same side, both sides experience day and night cycles. The exploration of the far side of the moon has provided valuable insights into our natural satellite, debunking the misconception that it is perpetually dark. Myth: there is no gravity in space. A common misconception is that astronauts experience zero gravity in space, implying an absence of gravitational forces. This myth arises from the weightless sensation observed during space missions, where astronauts float as if gravity doesn't exist. In reality, gravity is present everywhere in space, though its strength diminishes with distance from massive objects like Earth. Astronauts aboard the International Space Station (ISS) experience microgravity, not because there is no gravity, but because they are in continuous free fall around the Earth. The ISS orbits at a high velocity, causing it to fall towards Earth, but because it's also moving forward at the same time, it perpetually misses the planet, creating the sensation of weightlessness. This is similar to how a skydiver experiences weightlessness before deploying their parachute. Microgravity conditions allow scientists to conduct unique experiments, studying phenomena that are difficult to observe under the influence of Earth's stronger gravitational pull. Gravity on Earth creates the sensation of weight by pulling objects towards its center. However, in orbit, astronauts experience free fall, where they are constantly falling towards Earth, but moving forward quickly enough to stay in orbit. This creates the experience of weightlessness, or microgravity. Microgravity is an essential condition for conducting experiments in space, allowing researchers to study the effects of long-term weightlessness on the human body, fluid dynamics, and combustion processes. The misconception of zero gravity also ignores the fact that gravitational forces exist throughout the universe. For example, the gravitational pull from the Sun affects the orbits of planets in our solar system. Even in the vast regions of interstellar space, gravitational interactions between stars and galaxies shape the structure of the universe. Additionally, understanding gravity's presence in space is crucial for space missions. Engineers must account for gravitational forces when planning trajectories and orbits for spacecraft. For example, gravity assists or slingshot maneuvers use the gravitational pull of planets to increase a spacecraft's speed without using additional fuel, demonstrating the continued influence of gravity even in space. In summary, gravity is not absent in space. Rather, astronauts experience microgravity due to the continuous free fall of their orbit. This understanding is fundamental to our knowledge of space travel and the behavior of objects in the vast expanse beyond Earth's atmosphere. Myth: the moon has no effect on human behavior. One prevalent myth in both popular culture and folklore is that the phases of the moon, especially the full moon, significantly influence human behavior, causing people to act irrationally or unusually. This belief, often referred to as the lunar effect, suggests that the full moon can trigger a range of behaviors, from sleep disturbances to increased crime rates and even mental health crises. The idea of the moon influencing human behavior dates back to ancient times. In fact, the word lunacy is derived from luna, the Latin word for moon, reflecting the historical association between the full moon and madness. Tales of werewolves, who transform under the light of the full moon, and other supernatural occurrences have also contributed to the belief in the moon's impact on human actions. Despite the persistent nature of this myth, Scientific research has repeatedly debunked the notion that the moon has any significant effect on human behavior. Numerous studies have investigated the relationship between lunar phases and various behaviors, including sleep patterns, crime rates, and psychiatric hospital admissions, but have found no consistent or significant correlation. One of the most comprehensive reviews of the lunar effect was conducted by Ivan Kelly, James Rotten, and Roger Culver in 1996. They analyzed over 100 studies examining the moon's influence on behavior and found no evidence supporting the idea that lunar phases affect human actions. Their findings indicated that the perception of a lunar effect is more likely due to confirmation bias, where people remember events that fit their beliefs and ignore those that do not. Sleep patterns have also been a focal point of research into the moon's impact on human behavior. Some studies have suggested slight changes in sleep quality and duration during the full moon, but these effects are generally small and inconsistent. For example, a study published in the journal Current Biology in 2013 found that participants slept an average of 20 minutes less during the full moon. However, subsequent studies have failed to replicate these findings consistently, leading researchers to conclude that any potential effect of the moon on sleep is minimal at best. The belief in the moon's influence on behavior can also be attributed to the human tendency to find patterns and explanations for unusual events. When something out of the ordinary occurs during a full moon, people are more likely to attribute it to the moon's influence, reinforcing the myth. This cognitive bias, combined with cultural and historical narratives, perpetuates the misconception. Additionally, the moon's gravitational pull does affect the Earth, most notably in the form of tides. However, the gravitational force exerted by the moon on the human body is minuscule and not strong enough to influence physiological or psychological processes. The tidal forces that the moon exerts are the result of its gravitational pull on the Earth's oceans, a much larger and fluid system compared to the human body. In conclusion, the myth that the moon has a significant effect on human behavior is not supported by scientific evidence. While the moon does play a crucial role in Earth's natural processes, such as tides, its influence on human actions is minimal. Understanding the lack of a causal relationship between lunar phases and behavior helps dispel this long-standing myth and promotes a more scientific perspective on the natural world. Myth: stars twinkle because of their own light flickering. The twinkling of stars, or stellar scintillation, is a familiar sight in the night sky, often romanticized in literature and songs. A common myth is that stars twinkle because their light flickers as they burn in space. In reality, the twinkling effect is not due to the stars themselves, but rather the Earth's atmosphere. As starlight travels through the vast expanse of space, it remains steady and unaffected. However, when it enters Earth's atmosphere, it encounters varying densities and temperatures of air in constant motion. This turbulent atmosphere bends and refracts the light in multiple directions, causing the star's apparent position and brightness to fluctuate. This refraction creates the twinkling effect we observe. Planets, on the other hand, generally do not twinkle as much because they are closer to Earth and appear as larger disks of light. Their light also passes through the atmosphere, but the slight shifts are less noticeable compared to the pinpoint light of distant stars. The process of light refraction and scattering is influenced by various atmospheric conditions, such as temperature gradients, wind speeds, and pressure changes. These factors cause the light path to bend unpredictably, making the star appear to change position rapidly. This is why stars closer to the horizon tend to twinkle more than those directly overhead. The light from stars near the horizon passes through a greater thickness of the atmosphere, encountering more turbulence. Astronomers mitigate the twinkling effect by observing stars from high altitudes or using space telescopes. Observatories located on mountaintops experience less atmospheric interference, and space telescopes like the Hubble Space Telescope operate above the Earth's atmosphere, providing clear and stable images of celestial objects. Adaptive optics technology is also employed in modern telescopes to correct for atmospheric distortion in real time, using rapidly adjusting mirrors to counteract the effect of scintillation. Understanding the true cause of stellar scintillation enhances our appreciation of the night sky and the atmosphere's complex interactions. The atmosphere acts as a dynamic lens, constantly changing the way we perceive starlight. This phenomenon underscores the interplay between celestial objects and Earth's atmosphere, which, despite its beauty, can sometimes distort our view of the universe. The misconception that stars flicker due to their own light variations is rooted in early observational limitations and a lack of understanding of atmospheric effects. Today, with advanced technology and scientific knowledge, we can appreciate the true nature of twinkling stars and the role our atmosphere plays in this enchanting visual display. In essence, the twinkling of stars is a beautiful reminder of the dynamic and ever-changing nature of our atmosphere. It serves as a testament to the complexity of the natural world and the importance of scientific inquiry in unraveling the mysteries of the universe. Myth: you can't see the Great Wall of China from space. A widely circulated myth claims that the Great Wall of China is the only man-made structure visible from space with the naked eye. While this myth has a romantic appeal, it is not accurate. The Great Wall, although long, is relatively narrow and constructed from materials that blend with the natural landscape. Astronauts from low Earth orbit have confirmed that the Great Wall is challenging to see without aid. Other man-made structures, such as cities, roads, and airport runways, are often more visible due to their size, shape, and contrast with the surrounding environment. Photographs from space also highlight features like agricultural patterns and large-scale environmental changes, demonstrating that numerous human activities are discernible from orbit, albeit under favorable conditions and with the right equipment. The visibility of structures from space depends on various factors, including lighting, weather conditions, and the observer's eyesight. The Great Wall might be visible under optimal conditions, but it is not uniquely prominent compared to other large-scale human constructions. This myth underscores the challenge of seeing specific features from space and highlights the importance of context and perception in space observations. NASA astronaut William Pogue, who flew on the Skylab space station in the early 1970s, stated that he could barely distinguish the Great Wall without binoculars. Even with these optical aids, it blended in with the natural terrain, making it difficult to identify. Modern astronauts aboard the International Space Station, ISS, have similarly reported that other large structures, such as highways, airports, and urban areas, are more readily visible than the Great Wall. Additionally, advances in satellite imaging technology have allowed us to observe the Earth's surface in remarkable detail. High-resolution images captured by satellites can pinpoint specific buildings and even individual vehicles. However, these images are taken with sophisticated cameras and sensors far beyond the capabilities of the human eye. The myth about the Great Wall's visibility from space likely originated from a combination of national pride and the awe-inspiring nature of the wall itself. Built over centuries, the Great Wall of China is one of the most impressive engineering feats in human history, symbolizing ingenuity, perseverance, and cultural significance. While it may not be the only or most visible man-made structure from space, it remains an iconic landmark, celebrated worldwide. In conclusion, the Great Wall of China is not uniquely visible from space with the naked eye. This myth highlights the complexities of perception and the limits of human vision in the vastness of space. The advancements in satellite technology and astronaut observations provide a more accurate understanding of what can be seen from orbit, emphasizing the importance of scientific accuracy in our interpretation of iconic landmarks. Myth: the sun is yellow. A common depiction in art and media is that the sun is yellow. This myth persists despite scientific evidence that the sun emits light across the entire visible spectrum, which combines to appear white. The perception of the sun as yellow is primarily due to the Earth's atmosphere. When observed from space, the sun appears white because there is no atmospheric interference. However, as sunlight travels through Earth's atmosphere, shorter blue and violet wavelengths scatter more than longer red and yellow wavelengths. This scattering effect, known as Rayleigh scattering, removes some of the blue light from direct sight, making the sun appear more yellow or orange, especially near the horizon. During sunrise and sunset, the path of sunlight through the atmosphere is even longer, enhancing the scattering effect and causing the sun to appear reddish-orange. The true color of the sun, when viewed from space or an area without atmospheric interference, is white. The sun emits a spectrum of light that includes all the colors of the rainbow. When these colors are combined, they produce white light. This is why the sun appears white to astronauts in space. The white light of the sun is essential for life on Earth, as it provides the energy needed for photosynthesis in plants, which in turn supports the entire food chain. Understanding the true color of the sun helps us appreciate the complexity of light and the influence of the atmosphere on our perception. The sun's emission of white light, composed of all visible wavelengths, plays a crucial role in illuminating Earth and supporting life through photosynthesis. The misconception that the sun is yellow also ties into how we perceive light and color. Human eyes are more sensitive to yellow light, which can make the sun appear more yellowish to our vision, especially when it's high in the sky. However, scientific instruments that measure the sun's spectrum confirm that it is, in fact, a white star. This understanding also explains why the sky appears blue during the day. The shorter blue wavelengths of sunlight scatter more in the atmosphere, spreading out in all directions and giving the sky its blue color. Conversely, during sunrise and sunset, the sun's light travels through a thicker layer of the atmosphere, scattering more of the shorter wavelengths and allowing the reds and oranges to dominate. In summary, the sun is not yellow, but white. This realization underscores the importance of understanding atmospheric effects and the nature of light. It also enhances our appreciation of the sun's role in supporting life on Earth and its place in the broader context of stellar classification. Myth: meteor showers are falling stars. The term falling stars or shooting stars to describe meteors contributes to the myth that stars fall from the sky during meteor showers. In reality, meteors are not stars, but tiny particles from comets or asteroids that burn up upon entering Earth's atmosphere. These particles, often no larger than a grain of sand, collide with the atmosphere at high speeds, creating bright streaks of light due to intense friction and heat. Meteor showers occur when Earth passes through the debris left behind by a comet, leading to a higher frequency of meteors. The actual stars remain millions of miles away, and what we see are brief, beautiful displays of burning space debris, not falling stars. Meteor showers, such as the Perseids and Geminids, provide spectacular shows of light and are best observed in dark, clear skies away from city lights. Each meteor shower is associated with a specific comet. For instance, the Perseids are linked to the Swift-Tuttle comet. As Earth passes through the comet's debris trail, the particles enter the atmosphere and produce the dazzling light show. The scientific study of meteors has provided valuable insights into the solar system's formation and the nature of small celestial bodies. Meteors are remnants from the early solar system, and their composition can tell us about the materials present during the solar system's birth. When a meteor survives its fiery descent and reaches the Earth's surface, it is known as a meteorite. These meteorites are studied extensively by scientists to understand the conditions of the early solar system. The misconception of falling stars likely arose from the striking visual effect of meteors streaking across the sky, which can evoke a sense of wonder and awe. Historically, meteors were often seen as omens or messages from the gods, reflecting humanity's fascination with the night sky. In reality, meteor showers are natural phenomena that offer a glimpse into the dynamic and ever-changing nature of our solar system. They remind us of the vastness of space and the countless particles that travel through it. In addition to their beauty, meteors play a crucial role in our understanding of planetary science. By analyzing meteorites, scientists gain insights into the composition of asteroids and comets, offering clues about the early solar system. These space rocks contain minerals and organic compounds that may have contributed to the emergence of life on Earth. Meteor showers also provide a unique opportunity for scientific observation and public engagement. Astronomy enthusiasts and scientists alike look forward to these events, setting up telescopes and cameras to capture the celestial display. The study of meteors and meteor showers continues to be a field of active research, with each event potentially revealing new information about our place in the cosmos. Myth: seasons are caused by Earth's distance from the sun. A prevalent myth is that the changing seasons result from variations in the Earth's distance from the sun. This myth seems intuitive, since it aligns with the idea that being closer to a heat source should make a place warmer. However, while it is true that Earth's orbit is slightly elliptical, the difference in distance is not enough to cause seasonal changes. Instead, the tilt of Earth's axis is responsible for the seasons. Earth's axis is tilted about 23.5 degrees relative to its orbital plane around the sun. This axial tilt means that during different times of the year, various parts of Earth receive differing amounts of sunlight. When the northern hemisphere is tilted towards the sun, it experiences summer because the sun's rays hit this part of Earth more directly, leading to longer days and shorter nights. Conversely, during this time, the southern hemisphere is tilted away from the sun, receiving less direct sunlight, resulting in winter. This phenomenon is reversed 6 months later. During the northern hemisphere's winter, the southern hemisphere is tilted towards the sun and experiences summer. This axial tilt and the changing angle of sunlight create the seasonal temperature variations, not the Earth's proximity to the sun. The Earth's orbit is indeed elliptical, but the difference in distance between the closest point, perihelion, and the farthest point, aphelion, is only about 3%. This minor variation in distance does not significantly affect the overall climate. The understanding of axial tilt and its role in seasonal changes dates back to ancient astronomers. The Greek philosopher Eratosthenes, who also calculated Earth's circumference, observed the varying lengths of shadows at different times of the year and inferred that Earth's axial tilt influenced these changes. This understanding was further refined by later astronomers like Claudius Ptolemy. In addition to temperature changes, the axial tilt also affects the length of days and nights. During summer in either hemisphere, days are longer because the region tilted towards the sun experiences sunlight for a more extended period. During winter, days are shorter, and the angle of sunlight is more oblique, providing less warmth and shorter daylight hours. The concept of solstices and equinoxes also stems from Earth's axial tilt. The summer solstice, around June 21st, marks the longest day of the year in the northern hemisphere, when the North Pole is tilted closest to the sun. The winter solstice, around December 21st, marks the shortest day of the year in the northern hemisphere. Equinoxes, occurring around March 21st and September 23rd, are when day and night are approximately equal in length because the Earth's tilt is such that the sun is directly above the equator. Understanding the real cause of seasons enhances our appreciation of Earth's dynamic climate system and the intricate balance of astronomical factors that influence it. Dispelling the myth that Earth's distance from the sun causes seasons helps us grasp the importance of axial tilt in shaping our environment. This knowledge underscores the complexity of planetary motion and its profound effects on life on Earth. Myth: black holes are cosmic vacuum cleaners. Black holes often evoke images of all-consuming cosmic monsters, relentlessly sucking in everything around them. This myth exaggerates the nature of black holes, portraying them as cosmic vacuum cleaners. In reality, black holes are regions of space where gravity is so strong that not even light can escape, but they do not actively pull in objects over vast distances. The gravitational pull of a black hole is comparable to any other object of the same mass when you are far enough away. For instance, if the sun were replaced by a black hole of the same mass, Earth's orbit would remain unchanged because the gravitational force at Earth's distance would be the same. Objects must get very close to a black hole, within a region known as the event horizon, to be inexorably drawn in. Outside this region, black holes exert the same gravitational force as any other celestial body of similar mass. The myth of black holes as cosmic vacuum cleaners likely stems from their dramatic portrayal in science fiction and popular media. While black holes do have an intense gravitational pull, they don't indiscriminately suck in everything nearby. For example, black holes can have stable orbits around them, where matter can exist without being pulled in, just as planets orbit stars. Accretion disks, which are rotating disks of matter around black holes, are formed from matter that spirals in but is not immediately consumed. Black holes are fascinating and extreme manifestations of gravity, influencing their surroundings in intricate ways without acting like vacuum cleaners. Their formation occurs when massive stars exhaust their nuclear fuel and undergo gravitational collapse, leaving behind a singularity surrounded by an event horizon. This singularity is a point where gravity is so strong that space-time curvature becomes infinite. Observing black holes directly is challenging because they emit no light. However, their presence can be inferred from their effects on nearby matter. For instance, when a black hole accretes matter from a companion star, the infalling material heats up and emits X-rays, which can be detected by space telescopes. Additionally, gravitational waves, ripples in space-time caused by the acceleration of massive objects, were first directly observed in 2015 from the merger of two black holes. Another intriguing aspect of black holes is Hawking radiation, a theoretical prediction by physicist Stephen Hawking. According to Hawking, black holes can emit radiation due to quantum effects near the event horizon, causing them to lose mass and potentially evaporate over time. This radiation is significant because it suggests that black holes are not entirely black and could eventually dissipate. In conclusion, black holes are not cosmic vacuum cleaners, but rather regions of intense gravity with complex behaviors. Their influence is significant only within a certain proximity, and they do not indiscriminately consume everything in their vicinity. Understanding the true nature of black holes highlights the sophistication of gravitational interactions and the extreme conditions that govern these enigmatic objects. Dispelling this myth allows for a more accurate appreciation of black holes and their role in the cosmos. Thank you for joining us on this journey to debunk some of the most common astronomy myths and misconceptions. We've explored the real reasons behind why stars twinkle, why the Great Wall of China isn't the only visible man-made structure from space, the true color of the sun, and the fascinating nature of meteors. By understanding these truths, we deepen our appreciation for the universe and the scientific principles that govern it. Knowledge is a powerful tool, and dispelling these myths helps us see the cosmos with clearer eyes. If you enjoyed this video and learned something new, don't forget to like, share, and subscribe to our channel for more engaging content about the wonders of space. Stay curious, stay informed, and keep looking up.